Now, ionic bonding, Mr. Sands, you learned in our last podcast, is a bond between a
Metal.
metal to what?
Non-metal.
So we've got a metal bonded to non-metal getting attracted by the external electrons called the valence electron.
Yep.
So let's kind of dive in and get some more details
Okay.
on this. All right. The key thing, and we talked about this briefly in the last podcast, is there's a transfer of electrons.
Yeah.
They want to fulfill the octet rule. So here I have an element. We've got some internal electrons. I'll make them X's or something like that, or whatever. But this guy has got 2 valence electrons right here. This character over here has got 6. So they all want to achieve 8. So to achieve 8, the guy with the red, he can like give his 2 electrons away.
Right. So now the one on the right has 8.
And actually, this guy on the left
Wait,
has
how is
8.
how is 2 minus 2 equal 8, Mr. Bergman?
Well, it's because the lower level, we haven't really drawn that, but there would be 8. I'll put them as X's instead of dots. There would be 8 electrons in that previous level.
So 0 is equal to 8.
Yeah, that's
Interesting.
a fair way to
Okay.
say it.
All right.
0 is equal to 8 in the atomic world.
All right.
So these atoms are not happy. Happy? I'm happy. Go happy. Be happy.
Happy meaning 8 valence electrons.
8, yeah, stable
So
is a better word.
if the one on the left gives its 2 to the one on the right, 2 minus 2 equals 0, and 0 equals 8, the
Yeah.
one on the left, and then the 6 on the right plus
6
the
and
2
2 is 8.
gives us 8. Good.
And so
okay.
here you can kind of see I have drawn that. He's moving over to the side. And now something else important happens is that what happens is he gets a charge.
So if it loses the 2 electrons, it gets a plus 2 charge.
That is
because
correct.
Electrons are negatively charged.
And this guy gains 2 electrons symbolized by the red dots. And he gets,
A negative 2 charge
Negative
because
2
electrons
charge.
are negatively charged.
that's correct.
Cool.
Okay?
And
So-
then opposites attract. So the plus 2 attracts the minus 2.
Actually, let's go back and say something about that. Because what happens is actually, I think I drew this wrong, is this outer electron shell
Kinda
doesn't
gone,
exist.
yeah.
So he's going to be smaller with, say, 2 circles, and this guy's going to be bigger with all of his circles. But he's going to have a plus 2 charge, and he's going to have a minus 2 charge, and then they're going to attract to each other because opposites attract.
Yeah. Cool.
So that's what causes an ionic bond. Electrons transfer, there's opposite charges, they attract, they make a bond.
Cool.
Okay, some definitions just to kind of get some words out there for you guys. A halide is a salt that contains a halogen.
Halogen.
Now, what's a halogen? Mr. Sims?
Halogen are everything in group, the fluorine group. Fluorine,
17,
chlorine.
yeah.
Fluorine, chlorine, bromine,
So
iodine.
fluorine, chlorine, a bromine, iodine. That's pretty much it.
You can say acetine, but that's the rarest element in the universe, so you're probably not going to run into that.
Yeah. So if I have, so example, sodium chloride, there's that Cl there. But if I have, say, iron 3 bromide, that also would be a halide.
Right.
Okay. And crystal lattice,
Yeah.
okay, is a repetitive arrangement of atoms in an ionic compound. I just jot that down. We'll put some more meat on that in just
Yeah.
a second. One other definition, Mr. Sams, I think we probably should emphasize is the word salt. When you think of salt, folks, most of you are thinking of what you put on your French fries at lunch at McDonald's. But that's
French
not the
fries.
correct term in chemistry. What does the word salt mean?
Salt is equivalent to an ionic compound. Any ionic compound can be referred to as a salt. Now, table salt is sodium chloride, which is an ionic compound. Therefore, we can call it salt just fine.
Going back to the crystal lattice thing, Mr. Sams, a lot of students don't understand that either. And so I want us to take a tour to the Smithsonian Institution in Washington, D.C. Should we go there?
Let's do it.
All right, let's go to Washington, D.C. and see
Me.
Mr. Sams. Yeah, he was there.
We were there.
Yeah, we were there. I videoed it. Okay, we'll see you guys back in a minute.
So here I am inside the sodium chloride crystal, and we have alternating positive and negatives. The sodium being the red, the chloride being the blue, alternating positive, negative, sodium chloride, forever and ever and ever until you get to the edge of the crystal. There's billions and billions of these in just one little piece of salt like there is on your French fry.
That was pretty cool, Mr. Sams.
It's kind of fun being inside all that salt.
Oh, yeah. So, yeah, you can just see the one crystal connected to one crystal. So the Na connected to the Cl, connected to the Na, connected to the Cl.
It goes on.
And on.
And on.
And
And
on.
on.
And I could draw this
And on.
forever,
Yeah.
but I won't. In fact, there's a picture where it is drawn
Yeah,
with
so
like
you
little spheres.
pretty
That's-
much
Yeah, but it
saw
was
that.
cooler when you were inside of it.
It
I think.
was.
Yeah.
So yeah, one sodium for every chloride.
Yeah. So ionic compounds have particular properties, Mr. Sams.
Yes, they do.
One of the properties is that they are all solid at room temperature.
All right,
Why
let's take a look at a few of those.
Yeah, let's take a look at those. One property of ionic compounds is that they are solid at room temperature. They're all solid because they have strong bonds. And so they also tend to be brittle. We're looking here at some rock salt right here. These crystals here of rock salt. You also might notice that they're like a cubic shape. They have specific shapes and crystal shapes. So this is salt. If we move over to this next chemical, this right here is iron 3 chloride, and it's a yellow substance, and it tends to be brittle, so I can kind of break it off here, and you can see tiny little yellow crystals right there. And again, notice that it's also a solid. Our next chemical is a nickel 1 nitrate, and so it's green. Oops, sorry. And you can kind of see the tiny little crystals right there. They're flaky. If somehow we could super zoom in, we could probably figure out what their crystal shape is. It's hard to tell without some kind of a microscope. And then our last one is potassium chloride. It looks just like table salt as well, and it's all kind of very fine and granular, as you can see right here. Again, notice that it's also a solid. All ionic compounds are always solid. So, Mr. Sams, what state of matter are ionic compounds?
Solid at room temperature.
Always solid at room temperature. Could you ever make them a liquid?
You could make them a liquid. You'd have to heat them up really hot.
I think the melting point of sodium chloride is in the neighborhood of 3,000 Kelvin. It's something like that. So it's really hot.
Yeah.
So yeah, okay.
All right, so here's some properties.
So let's talk about each of these. You may just want to pause the video and then jot these down. You do need to jot them down.
Yeah.
But we already kind of talked about that. They have high melting point. That means they're solids.
Right, and that's because there's a very strong attraction between the positive and negative ions.
Remember that when we had, let's say we had the calcium, I think that was calcium, we didn't honestly say it, and we say you got the O negative 2. That negative attraction for the positive is a very strong bond. Mm-hmm. They don't conduct electricity when solid. So if you like stick a
conductivity meter or something,
or just stick a ionic compound in an electric socket, you won't get hurt unless it's wet.
True.
Don't try.
I wouldn't recommend it, but
so because the electrons can't move,
right,
the electrons
they're
are
fixed on those ions. However, if you heat them up to their molten state, to where they become a liquid, then they do conduct electricity. So don't pour molten sodium chloride into your.
You're ahead of the game, Mr. Sanders. That, of
socket.
course, is what I say here.
Oh, hey, look at that.
Good conductors when dissolved or liquid.
Yes.
Yeah.
So dissolved meaning dissolved in water.
So like if you take salt and you put it in water, it dissolves, right? And it tastes salty water. It tastes nasty. So that conducts electricity really well, and you'll learn about that later in the year.
Yeah, solutions
on solutions and stuff.
Yep.
They're also brittle and hard, and so you saw that when I was messing around with them, that they're brittle. That means they can shatter very easily, and that's again because of their strong bonds. What causes them to be attracted? I think we've already addressed
opposites
this.
attract. Positive attracts negative.
Yeah, opposites attract, right? That's the key thing to understand here. Opposites attract. Opposite charged. A tarked. Yeah, they're tarked. Hey, we want to just do one quick thing. Is how would you draw a Lewis structure of a particular couple examples?
Yeah, of an ionic compound.
So let's do something relatively easily. We'll do calcium and then chlorine. Okay. Now calcium, if you were to draw his Lewis structure, has 2 valence electrons.
Okay.
Now, chlorine, now I'm looking at the periodic table. How many valence electrons would that have?
7 valence
So use
electrons.
that chart that we did in a previous podcast. So he's got 7.
That's
now,
6.
And I've got 6, thank you. So is anybody happy?
No.
They want 8. So the calcium, he can give away 1.
Right.
And he's made the chlorine happy.
The chlorine is happy, but calcium still has the extra one.
So what do I do?
Let's throw another chlorine in the
mix. But if you take
here.
another chlorine in the mix, you see, this kind of determines the ratios, in fact.
Yeah.
This electron can go to the other chlorine.
Oh, okay.
And so then you'll have calcium with a +2 charge and no electrons. Remember, 0 equals 8. And then you've got chlorine now with 8 electrons each. Actually, it's not chlorine, but...
No, it's chloride because it has a -1 charge.
Because the -1 charge is there. Yeah.
Mm-hmm.
And
there.
That's it. So it's like a series of 2 pictures. You show the element symbol, like calcium over here with the number of dots. You show the arrows moving, and then you just kind of show this, and then the opposites will attract.
Yeah.
Well, let's the next one do iron 3 oxide. Now, we haven't exactly learned about what that 3 means. It means that it's got 3 valence electrons. So iron is Fe, and there are 3 electrons on it.
Right.
Now, how I got that, it's a
Don't
little
worry about it.
confusing.
Yeah.
Iron is right here on the periodic table, and
You're
he
probably thinking,
sometimes
"What?"
he has 3, and sometimes he has 2.
Yeah.
How that is
Don't
a
worry about it.
discussion for later. But the other chemical is oxygen, or actually oxide. But if you look at oxygen on our table for valence electrons, there's 6 valence electrons. So if I were to draw 6 valence, you know what I'm going to do a little different. I'm going to do X's. Then it's easier to know where the oxygen,
Okay.
the atoms or electrons move.
Okay.
Oh, I'm drawing extras. I shouldn't show
That's
you
right.
that. So, is the oxygen happy?
No, he wants 2 more.
He wants 2 more. So if
But
he-
iron has
Iron
some to
has
give
some to give him, so he can give 2 of them. But you see, unfortunately, the iron is still unhappy. He's got 1 additional one.
him. Yeah.
And so he can give 1 of them to a second oxygen.
But now the oxygen is
now
not.
the oxygen is happy. So we can have another ion
Okay.
with his 3 dots.
Hey, look, he can give
he
one of
can
his
give
dots.
1 here. And now the iron's still unhappy, right?
But if we do another oxygen,
With his
6.
6 X's, right? Guess what? He can give away his
Those 2.
2 electrons.
now all the irons are happy. 'Cause
Everyone's
0
happy.
equals 8, and all
Yeah.
the oxygens are happy because they
It's
all have
8
8.
equals 8.
So
So
let's
it's like
draw it.
this. You've got Fe.
Each of
plus
them lost 3 electrons, so plus 3. Yep.
And then each oxygen has 8 electrons. I'll put 6 as X's and 2 as dots.
That
to
came from the
indicate
iron.
They came from the iron,
Right.
right? An electron's an electron. So this is just for our sort of accounting purposes that I'm drawing them this way. But 2 of them came from the irons, and then the 6 of them belong to them. And so this is the 2 pictures that illustrate why the bonds work.
All right.
All right, that's
I
it
think
for
that's
this
it,
podcast.
yeah.
Not much there. You'll be doing some examples like this in your homework.